All right, everyone, we are back for another episode after quite a prolonged hiatus here. I was at a few conferences, and then I was on vacation, and then we got hit with a hurricane here in Houston. As Professor Julian West, or I'll start saying Julian now. As he knows, we just got hit with Hurricane Beryl. It was only a Category 1, but I am still without electricity. It's been 5 days. If you're a part of the Texas government, or the Texas infrastructure, I don't really get how it's so bad. But I don't know anything about transformers and electricity, though, so I probably shouldn't really speak on that. But with that, though, we have our power here, so I'm really, really happy to be joined by Julian here today to talk about his background, but also just the fantastic chemistry. And also, one other thing I'll say is that congratulations is in order. You just were honored with the Talented 12 for 2024, so congratulations to you. Really looking forward to kind of seeing that come together, so welcome.
Yeah, thank you. It's wonderful to be here. I was really excited to get your invitation, after seeing the wonderful list of people that have been on the podcast before.
Yeah, it's really weird now. Actually, this is the first podcast I'm recording since being back from Texan, and I actually got recognized by two people there, so that was really interesting. It's cool to see this platform really kind of take a shape. And I've said this before, but chemistry is a field that deserves all the praises. So, if I can help to do that, and I think that would be absolutely fantastic. So,
right.
Just ready for another fantastic episode today. I guess we'll start with your background. You did your undergrad at University, British Columbia, Vancouver. Mm-hmm. I gotta get up to the West Coast, Pacific Northwest, United States, Seattle, but also Vancouver. It's not a convenient plane ride. I don't know if there's any direct flights, but it's a fantastic city from what I've heard. And just I presume you then grew up in maybe Western Canada, but I'll kind of let you take a little bit of your background.
Yeah, for sure. So first, I'll confirm that Vancouver is beautiful, and actually, there are several directs from Houston to Vancouver International.
Okay,
so
I'll keep that in mind.
Yeah, not too bad. It's about 4.5 hours, but
okay, that's not bad.
But yeah. So it's always green. It's a lot more sort of evergreens there. Beautiful mountains, which definitely I miss a little bit living in Houston. And
very flat here.
Yeah, but yeah. So I guess I've lived in a few different places. So I was actually born in Utah, in Salt Lake City, so the Mountain West. But then I spent a lot of my time growing up in Edmonton, Alberta, some people may be more aware of this year because Edmonton was within one game of winning the Stanley Cup. The
reverse
hockey.
Sweep was unfortunately.
Yeah, it was thwarted.
I send my condolences to you. I'm actually looking at a map right now. I need to center myself. Where is Edmonton on here? How far
so basically,
east do I got to go?
Edmonton is basically you start in Montana and you just keep going north. So
okay, way north of Calgary. It's directly north of Calgary.
Yeah, it's directly north of Calgary. So
you said you grew up in Edmonton?
Yeah.
Okay.
Yeah.
Okay, I have a question about that then, because a lot of these, Edmonton's kind of out. It's a city, but it's kind of out in the sticks. So, there's virtually nothing out there. What's kind of been the, kind of growing up where it's it's a big city, but it's very secluded, right? I mean, if you wanted to go, if you want to go down to Calgary, I'm sure it's not a necessarily convenient drive.
That's a 3-hour drive. I mean, basically, you make one turn the entire drive because it's just a straight highway through the fields. But no, it is interesting because it's a city of a little over 1 million people. But between Edmonton and Calgary, it's about 3 hours of canola fields.
Right.
So no, it's interesting for sure. But I think one thing that's nice about sort of being in one of these sort of more open areas is that there's a ton of nature in Edmonton. So there's this river that runs through the North Saskatchewan River, and basically there's this beautiful series of parks that go all the way around it. So yeah, it was really good, walking, running, mountain biking, and yeah, no, it was a cool place to grow up, and literally very cold in the winter.
I was gonna say, yeah, I'm looking at a map right now. It's literally just like I mean, they have that quaint little square. You have the couple loops, and then you literally have a river that goes diagonally through your city.
Yeah,
that's pretty cool.
Yeah.
But it is a bit funny because I'm sure you have, some people down here in Houston. It gets to like 70 degrees and already put on the winter coat. I literally know people that do this in Houston that throw on a winter coat at 70. And to each their own, but I think it's hilarious that he'll even know.
I kind of do that now. I've lost a bit of my cold tolerance, but yeah, no, I mean, definitely, I'd say one of the, really unique experiences of being in Edmonton when I was in high school, it was in, the depths of December. There was one day when it was actually colder in Edmonton than it was on the surface of Mars.
Oh my God.
It was minus 57 on Mars.
Like no wind chill? Was that on top of the wind chill, or is that like
that's
no
without
wind chill?
The wind chill.
Oh
yeah,
my!
It was
God.
minus 58 in Edmonton. I mean, it doesn't usually get that cold, but
right, yeah.
But it does get pretty far into the negatives there, and yeah, it's interesting. Definitely worth experiencing at least once.
Yeah, I think. Well, it's got to humble you for sure. It's like, oh my God, like I'll never. It's definitely a humbling experience. Because I complain about the Northeast sometimes, like being from Philadelphia and New York, but I've never been to, Toronto's not even as north as Edmonton, so but up more north.
Yeah, but that's cool. And then the other fun thing, right, is that in the summer it's like, 85 degrees is like a hot day,
right?
But the other,
I'm sure the nature.
Yeah.
Oh, go ahead. Sorry. Go ahead.
Yeah, the nature. And then the other thing is, the further north you get, or the further away from the equator, the bigger the difference in the length of the day.
Mm-hmm.
So it's like, in December, the days are super short. It's like, the sun comes up at like 9 or 10, and, then it's basically set at 4 or 3:30.
Yep.
But then in the summer, it's like the sun comes up at like 4 a.m. and it doesn't go down until almost midnight. So it's
people that are close to the equator, especially even the subtle differences between where I grew up in the Northeast and in Houston, there's something about your mood changing, right? So when it gets dark earlier, like you're in the wintertime, I feel more moody, and I don't. It's got to be contributed to the the length of the day, I think. So I don't know. For you, like in the wintertime when you have those short days, I mean, do you feel yourself kind of being more, I don't know if moody is the right word, but but in the summer when the days are longer, I don't know if you kind of feel the same way, but.
Yeah, I mean, definitely it's a different feeling. I think one thing that was really important in the winter, to really avoid getting too down in the dumps was, to kind of really lean into that kind of cozy feeling, I guess.
Oh yeah,
very
true.
Like, make a fire in the fireplace and, have some tea or hot chocolate or coffee and, that kind of, I think it's called hygge, that kind of coziness.
Mm-hmm.
Yeah. So actually, yeah, that's one thing that I kind of miss about, the more serious winters is,
right.
Again, like that coming in from the cold and having that, nice fire. But then again, I've lost a lot of my tolerance. So now, 60 degrees is pretty cold here.
No, that's some good stuff. Now, so coming up, through, junior high and high school, I mean, obviously there was nature, but,
right.
Were you always interested in kind of in STEM, or what were some other hobbies that you kind of like to take part in coming up?
Yeah, so I think I was always pretty interested in science and to a degree math as well.
Yeah.
Math became less interested in me as I made it further through my schooling, but yeah, definitely it was really interesting to learn. I think like high school physics is always a lot of fun. You calculate an equation and then you actually throw a ball and see, oh yeah, it does stay that long in the air, or it does go that far or whatever. But yeah, I was interested in that. um, Actually in high school I was the least interested in chemistry, and
Yeah.
chemistry was actually my worst science. So yeah, so definitely wasn't predicting to go into chem.
Mhm.
But yeah, outside of that, I was a huge band kid. So I
Okay.
played trumpet and percussion in the concert
Mm.
band, and played in some high school bands as well. I played the bass, but I also like playing guitar and piano.
Oh
And
wow, so you're very
so
musically inclined.
yeah, music has been a really and continues to be a big part of what I like to do and who I
Yeah.
am. Actually, that's the reason why I actually have a real microphone and headphones.
Yeah, we were chatting beforehand for the audience. I was like, I think Julian's the first guest I've had on here that's actually had like a real microphone. So this is actually
Uh-huh.
quite. Hopefully, you're getting really good audio quality right now. You
Yeah.
could thank Julian for
Uh-huh.
that. But yeah. So how, you know, you mentioned that you play all these instruments coming through. I know a lot of chemists who spend a lot of their time, their hobbies is within music, and I'm actually one of the only ones that like I'm kind of musically illiterate. I don't really, I unfortunately actually don't play any instruments. I kind of take my time in sports, but when people I talk to that like to do instruments, I mean, it's got to be something about that pattern recognition, and that's just. I mean, it's a whole science of it itself, really. I think, and it's just beautifully the way music it sounds. Now, have you kept up with instruments you played with since high school, or are you kind of taking on you know, new instruments, or what's kind of been recently? What have you been playing?
Yeah. No, I mean, I think first off, like you were saying, yeah, I think music, but all these hobbies, can have a huge benefit on not just our ability to do science, but, just to live like a fulfilling life too.
Yeah.
But, definitely with that pattern recognition, yeah, being able to recognize a chord progression you know, uh, or, or sort of where a melody line is going, that can really translate to, that same kind of thought process of, working through a mechanism. But,
Yep.
certainly I think in sports, again, it's like, if you're climbing a rock wall, how do you get past, this one, puzzle? Where do you put the holds? Where do you push? Where do you pull? Or, in soccer, where do you thread that ball through the defenders? How can you get them
Yep.
to move how you want? And, and that's something that's been really important for me, is having that space to keep going with these hobbies. And that's something that I've really tried to pass on to my group as well. I think one of the things that I try to say to everybody in our group a lot is that again, being chemistry is just one part of who we are. Again,
Right.
it's a really important part, because we've all made the choice to be here. But
Yeah.
we also need to make sure that we're really you know giving time and effort in these other areas that are just really important for being a rounded person. um yeah, so with that, yeah, I do keep up with music, kind of sporadically. I'll go through a phase where I'll play quite a bit of piano, and then I'll pick up the guitar. And um I guess more recently also I listen to a lot more music because it's a good thing to do in the background while you're writing or
Right.
doing other things.
Hmm. I absolutely cannot be writing without music on or
Uh-huh.
and something in the
Uh-huh.
background. Recently, I've been putting on like the I've been putting on Coldplay's greatest hits as I write. That's
Oh
kind of been my
yeah.
thing recently.
Yeah, I
Um,
actually, yeah, last month, I got this nostalgic feeling for Coldplay, and I just
yeah,
went through their albums again. And,
yeah,
it's like they wrote some good stuff. It was like a rush of blood to the head. It's like I remember
right,
every song on this album.
yeah. You almost not even just Coldplay, but you forget how many. Well, all right, I'll speak on Coldplay have so many bangers. It was like, oh my god, I forgot how many bangers you have.
Yeah, yeah,
And I feel like, but you kind of get that feeling from a lot of bands and artists you haven't listened to in a
mhm.
while. It's like, oh my god, you forget like how many hidden gems there are. And so, yeah, if you're in whatever you're writing, put your suggestions down in the comments. I'd love to let's see what people are listening to while they will do
Uh,
whatever with chemistry. Honestly, you don't have to be
yeah,
writing, but if you're at the bench
yeah.
top, let us know what you're
No,
listening
for
to.
sure. I mean, it's like when I was a graduate student, I would say, who is it? Probably, I should have put an acknowledgement to, Weezer and Fall Out Boy and, a few other bands just for, getting me through setting up all those reactions.
Right. I can just hear it now, sitting at the glove box and setting up your, even sometimes setting because people that like, maybe don't work in glove boxes, but setting up those like 4 mil scintillation vials
Hmm.
inside your glove
Hmm.
box, it takes time to measure everything out. You think it'd be quick, but it honestly takes you like 30 minutes, to
Yeah.
just weigh everything out. So, and dispense your solvents. So you can, time can fly when you're sitting at the glove
Yeah.
box doing stuff. So, yeah, I definitely hear that. One other thing I wanted to comment on because you raised a good point is kind of having your hobbies outside of chemistry because you
Hmm.
are right. I mean,
Hmm.
when you make the decision to go to graduate school, it takes you are inherently taking on difficult work, and
Yeah.
you certainly
Yeah.
can love it. And I feel like people forget though because this is just academia in general, not even just in chemistry, but you are surrounded by some of the best minds that think about chemistry all the time. So you have this like almost like false sense of like kind of ethic, but like people that love chemistry. So like I feel like it's a little bit disparaging if you feel like you're not working up to that. But you just got to remind yourself that like people's hobbies are chemistry all the time. They're thinking about it all the time. So don't kind of compare yourself to maybe those people. I'm not saying don't work hard or anything like that, but like just keep those hobbies and activities in mind, and to make
Right.
yourself like a full person. That's kind of my opinion on it. Take it with a grain of
Yeah.
salt for anyone listening.
No,
But
I mean, that's absolutely, what I agree, or I absolutely agree with that as well. And one thing that I would say, also, well, two things on that. One is that, at least in my lived experience, when, yeah, I definitely felt a lot of that pressure very acutely at the start of graduate school,
right,
not really from my advisor at all,
yeah,
Erik Sorenson. He was very supportive, very, very much about people, but really from, yeah, my coworkers, that sort of peer pressure of, when the lab next to you, has, a 70-hour work week, you kind of feel that, oh, should I be going home right now? But
right,
what I found is, when I was trying to, match those hours or get close to them, again, I was just like so tired. I was making mistakes, I was forgetting to add reagents. I
yeah,
was making the most useless screens, those like, 5, 6, 7, 8% loading screens. And it's just like, my science was terrible. And also my health was terrible. I gained like 20 pounds.
wow,
And yeah, it was just like, I got to this point where it was kind of like, I've got to make a change because this is not sustainable. And I think the biggest change I can make is, one, to cut back those hours, bring back those hobbies. So, start running again, start playing music again. And yeah, and just see what happens. And what was really amazing is that when I did that, when I was working more like 40 hours a week in the lab, the chemistry started working, which was, again, I had that space to actually think, not just what is an experiment I could run, but what's an interesting experiment I could
Right.
run? What would tell me something? So yeah, so for me that was super transformative. And again, that's a place where I really want everyone in our group to be able to be. But yeah, the other thing that I'll say, and again, this is with a little bit of the benefit of hindsight, and now also being on the other side, as an advisor, and also as a postdoc, is that, again, I think that, if you aren't looking too carefully, it will, definitely, it seems like, especially as like an incoming graduate student, it's like, oh, everybody around me is like so intense and they're working all the time. And, like, oh, I've got to keep up in all of this, and definitely there are some people that sometimes work all the time. But, as I went through graduate school, what I started to realize is that, some of these people, that I thought were working all the time, and were really sort of giving me that kind of implicit pressure, sometimes they were leaving at, 2 p.m. on some days, some days they weren't showing up until noon, and it's like they weren't actually working all the time, you know.
Right. Hmm.
Sometimes they were working really intensely. Sometimes they were, working odd hours. But, in reality, it's just not really realistic for
Right.
most people to do that. So it was just kind of like, realizing that, oh, it's actually like, I'm not being lazy or whatever, and that actually the standard that I thought that I had to hit when I came into, graduate school is actually a standard that almost nobody is hitting.
Right. Yeah, those are great points. Yeah, thank you. Also, yeah, thank you for sharing your experience with that because it's so important to hear, I think, particularly for, well, graduate students now and incoming graduate students, because there's a lot of truth to it. Anecdotally, I noticed that people, graduates in general, not even just chemistry, but they, people will neglect your physical and mental health, right? And
Yeah, yeah.
like, I'll say, I've said this a billion times and I'll keep saying it. You can't, it's hard to do really stellar science if you're not physically well, you're not mentally well. Like, you just can't do it. You got to keep those things in check. You got to make those a priority, really, ahead of the science, I think.
Yeah,
And
yeah.
I've noticed that when you take care of those things, your science it comes into order. I've noticed that this is anecdotally for me.
Right.
When those things are in order, like the science begins to kind of work.
Yeah. Yeah, no, absolutely. And I think one other thing that, I think can also help with, sort of growing in that area is to really just approach it like an experimentalist. So, there isn't like one recipe, it's like
Right.
what really, gave me, all that sort of, enjoyment and, ability to sort of unwind and relax, that's not going to work for everyone. But basically, it's like knowing that, giving yourself that space to try things. If you feel like something isn't working, like try something different and see how that feels. And then, again, it's like just change the variables until you, hit a good equilibrium. And
Yeah.
I think, again, we know the process from our reactions and, we can use that skill in our lives as well.
Yeah. So I think this will definitely be reassuring for a lot of students to hear. So thank you for sharing that, Julian. Yeah, it's
Yeah, of
very
course.
insightful. Seriously. But kind of I guess getting back to it because I'm sure
Yeah.
we'll touch on those subjects all the time. But
Uh-huh.
you went to UBC Vancouver, so you moved from Edmonton to UBC. Anything in particular reason why you went to Vancouver? I'm looking at it now, though. I will say it's right there on the lake, like it's right on the peninsula. I think, right? So it's got to be beautiful scenery there.
Yeah, right on Point Grey. Yeah, it's super beautiful. So yeah, it's up on this cliff, and actually, yeah, you can hike down to some beaches around there. Yeah, and you're right on this big sort of forest endowment land. And yeah, actually, the campus is pretty beautiful as well. Shows up in a lot of movies too. I
Really?
remember, Yeah, so Vancouver is actually a huge place for film and particularly TV. So, yeah, so I think when I was an undergrad, they were filming Human Target a lot there. But yeah, like the X-Files were filmed there, like a lot of, you'll see like on campus, like police cars that say NYPD because, it's supposed to be New York. Yeah, I walked past Shia LaBeouf one day on the way to class. So,
You did, or are you saying you know someone that did?
yeah, yeah, I did.
Oh
Yeah,
wow.
they were filming in the chemistry building because actually the chemistry D block is this really old, beautiful building that often stands in for Harvard
Really?
in movies. So,
They can't just go to
but
Harvard itself. That's funny.
yeah, but yeah, but it's yeah, it was really beautiful there. I think one thing that drew me is wanting to get a little bit further from home. So so when I grew up in Edmonton, I grew up 2 blocks from the University of Alberta, which is a really good Canadian university. But, for me, it was just literally too close to home,
Yeah.
2 blocks away. And so, there was a little bit of that idea of, I want to go somewhere different, to experience something different, but also to not go too far. So,
Right.
so Vancouver is about a 13-hour drive. So you've got to go through the mountains, through the Rockies to get there. But yeah, it's like a hour 20 plane ride as well. So, I knew that it was, or to me, it felt like it would be this good balance. And again, it's like super beautiful, some really good food. And yeah, it was a cool adventure.
Yeah. And so while you're at UBC, is
Uh-huh.
that when you really your chemistry interest really started to take form? Like,
Yeah.
how did that kind
Yeah.
of opportunity or
Yeah.
that start?
Yeah. Yeah. So definitely that's where my personal interest in chemistry, really grew a lot. So, in full disclosure, there was a strong family pull towards chemistry. So my parents are actually both chemists. Uh, they were a grad school couple in Wisconsin, actually. So, yeah.
Look at that.
So definitely I knew from growing up that, chemistry could be like a reasonable, profession. It's something you could actually do for your work.
Right.
But, definitely we didn't talk very much about chemistry in the house, much more about, music, school, whatever.
Don't
And
take
my
your work
parents
home.
never never pushed it, but, I always knew that this was like a possibility.
Right.
But, so I came into undergrad and I was, really interested. I was really interested in biology, and I still think that biology is really, really incredible. These chemical reactions can give rise to, these super complicated, collections of cells and, you know, and then on the like organism level, like communities, ecology, it's like super fascinating. But
Nature is the world's best chemist. I
yeah,
know.
yeah, yeah. I mean,
Quite
nature
literally.
is amazing. But it was really in my first year. So at UBC, in the second half of your second semester in the first year, that's the first time that you take organic chemistry. And once I was liking everything all right. I was enjoying physics, and Gen Chem was fine. But once we got to that organic, it was kind of, one, I had a really good teacher. Um, yeah, Rudick, who really brought a lot of enthusiasm to the topic. But you know, the other thing is that he just had a really good way of presenting it.
Hmm.
So it's like the the reactions make sense.
Right.
It's not like, oh, this is a weeder course to keep out all the pre-meds or whatever. It's like very much he was presenting it like, you know, these are like simple principles, and and if you follow them, you can understand everything.
Right.
And, and just watching that, the SN1, SN2, E1, E2, conformers, ring flipping, it's like, hey, this actually makes a lot of sense and this is pretty
Right.
cool. So, that got me interested enough to become a chem major. And, I'd say it was really just some really great teachers and mentors that, kept me in chemistry after that. And
Yeah.
it really made me glad to have made that change.
Hmm. Yeah, I definitely I hear everything you're saying because my undergraduate organic professor, who eventually became my undergraduate research advisor,
Hmm.
Professor Lloyd Baston, I mean, the way he was so enthusiastic about teaching
Yeah.
organic chemistry, it's just something you really can't. It's something that you can only emulate. It's like something you take with you as you go, and like just remembering that kind of enthusiasm, it goes a long way.
Yeah.
And
Well, I mean, yeah, I think enthusiasm and just like also, one thing that really stood out to me and is something I've tried to bring as a teacher as well is, it's just to always keep this view that, chemistry and, particularly, at least for me, organic chemistry, this is something that's for everyone. You know, everybody can learn this,
right,
it makes sense.
yes,
It's going to be a different process for different people, but
right,
again, this is a really cool, beautiful science, and
right.
yeah, everybody, everybody has that ability.
I I think there are some people in across the world that kind of treat organic chemistry like a weed out course, and they have
Uh
that
huh.
mindset
Uh
going
huh.
in. I really wish we could erase that because, like you said, I really think organic chemistry could be for everyone. It doesn't have to be an elitist course, if that makes any sense. Like
Yeah.
when people take
Yeah.
organic, they're like, "Oh my god, you took organic? That was so hard." Like,
Yeah.
I don't know.
Yeah.
I don't really buy into that. Now, of course, I have a bias though because we're here now,
Yeah.
but I don't
Yeah.
know.
I
I
mean,
think it could be for everyone.
it is hard, and I think the
Right.
one thing that does make it hard, one of the things is that it is super different from
Yeah.
everything that you've taken up to that point. But I because really it's more sort of like logic and language than it is balancing stoichiometry and equations. So
Right.
but I think that's one place where you know an instructor or a professor can really make a difference, is navigating that sort of introduction and transition.
Yeah. Yeah. Because I think for them, I mean, there are some things you have to memorize. Like there are a couple of
Hmm.
things you
Hmm.
got to memorize, you got to know. But it really is the first time for an undergraduate student or whoever's taking it that like you have to think outside of the box. Like you literally can't memorize everything,
Yeah.
and the way you think about even like I remember the first time learning about retrosynthesis, like
Uh-huh.
like you like learning about retrosynthesis. There's no comparison in any other course I've ever taken up to that point. Right, it's the very first time. I
Right.
don't know if you kind of agree with that or disagree with that, but I just don't. I don't know. It's I don't think it's comparable really to anything.
Yeah, yeah.
You
No, I
know?
mean it's super super mind bending. Again, it's like thinking forwards and backwards, right?
Yeah.
And
And organic molecules they're like a puzzle, right? So like you have to start to think that way, and it really pushes the boundary, I think, of what your brain's capable of the time, right? At that point, right? If you're 18,
yeah,
19 years old, very first time taking organic, like, man, it's definitely a different feeling. You can't just get by
yeah,
memorizing stuff on the exam,
yeah. Well,
for the most
I
part,
think
anyways.
yeah, particularly for that retrosynthesis and and forward synthesis, and those synthesis questions on exams. One thing that I think, and also mechanisms.
Yeah.
One sort of habit that I think was really cool that that I started developing in organic when I was an undergrad, and I try to have for students when I'm teaching as well, is that sort of idea that yeah, you can't have it all in your brain at once. You're not going to just like Mozart or whatever, write down the first draft and it's perfect. You're going to have to try a lot of things, iterate, go to a lot of dead ends and be like, okay, I've got to start from some different place. And just
Literally.
getting that kind of comfort with, you know, trying things, them not working, and then trying something else. I think it's really cool that that's actually something that you almost need to do in organic chemistry, and you sort
Yeah.
of get a head start for when you get to the lab, and that's literally what you're doing with setting up all these test reactions. So
Right.
just sort of getting that comfort with experimenting, first with the pen and paper, then in the lab, I think is a really cool part of the undergrad organic sequence.
Right. So while you're at UBC, you mentioned you had done undergraduate research,
Yeah, yeah.
with Professor Glenn Sammis. So
Uh-huh.
you want to tell us a little bit about maybe things that you did, but also how the opportunity arose for you to do undergraduate research and
Yeah, yeah,
to do that?
yeah. No, so yeah, interestingly, or maybe not interestingly. So, again, yeah, my undergrad transcript was not straight A's. Definitely far from that. I had a reasonable number of A's in chemistry, but I have 1D, a C minus, a few other things. So again, I wasn't like some straight A student that everybody was begging me to join their labs, but yeah, I really liked organic chemistry, and and I was interested in trying to get some research experience at UBC. So I was asking people, and I asked some of my professors, oh, who does who would be good for organic chemistry research, and a name that kept popping up. And also I asked my TAs when I was taking
Yeah.
the lab courses, and and one person that there was never anything negative about was Glenn. So
Fair.
so I basically sent an email, and this was in my third year, so I guess my junior year, so a little bit later for chemistry research than a lot of people. I was just like, oh, I'm interested in research, could we, do you have any opportunities? And then Glenn wrote back and said, yeah, let's meet up. And yeah, I had so I got to his office, and what was really, really apparent, like that stuck out immediately. And this was also something that, I'd heard about from, the TAs that I talked to, is just that, Glenn is all about, one, super enthusiastic, but two, he's, all about the people, and people
Hmm.
being excited about chemistry. And so, I got a really good impression there. He took a lot of time, to talk to me about, what I was interested in, why I wanted to do research. And then, after all of that, again, I didn't have like the best transcript. But at the end, Glenn's like, yeah, I wasn't sure if I'd be able to take an undergrad, but let's I want you to do some summer research, and we'll find a way to make it work. So,
Cool.
we were able to scrape together some funding, and really him taking that chance, was what really started me on this whole trajectory.
Yeah.
Because, again, partway through graduate school or undergrad, again, in the first half of undergrad, it was a little rough at times. I did have a lot of challenges in my second year. And there was a time in that second year where it's just kind of like, do I even want to finish this degree?
Wow. Mhm.
So definitely sort of going from that, and then having this really transformative experience in Glenn's lab in the summer, and then Glenn's enthusiasm and support and really encouraging me to not only go to graduate school, you know, so over the summer I was like, okay, maybe I'll try to go to graduate school in Canada, maybe I'll try to go to Ottawa or maybe University of Toronto if I'm ambitious, but it was really Glenn who said, yeah, I think, you should, I think, you really have the ability to go to graduate school. And I think that you should apply to, not just, these really good programs, but also like these really prestigious programs,
Right.
and it was Glenn who encouraged me, apply to Princeton, apply to Caltech and all these places. And yeah, really just that encouragement, got me to submit the application. And then his huge amount of support got me some really amazing opportunities to actually do graduate work.
Yeah. Wow, that's incredible. Thank you for sharing that. Because I think a lot of people get the impression that, and particularly professors, that their undergraduate and graduate experience were just hunky dory, fantastic,
Yeah.
and
Yeah,
so
smooth
thank you.
sailing.
Yeah, so thank you for sharing that, because a lot of people are going through challenges, especially life is going to happen, undergraduate and graduate. So like, it's just, it's not all smooth sailing and perfect, So thank you for sharing that. Um, I think that's really refreshing to hear that your undergraduate advisor did that, because what a great opportunity.
Yeah.
And I'll say this: I'll never forget, like, some of my fondest memories in my entire life, honestly, was that summer of just doing undergraduate research.
Right.
I was just doing undergraduate research with my advisor over the summer. I had stayed, we got some funding for me to stay in the dorms. So I was just living on campus by myself, doing undergraduate research. I think it was only me at the time too, just doing research and just living on campus. Like, just such a fun, chill time, such a great summer. So
Yeah. No, I know for me, that summer, in Glenn's lab was just kind of magical in a way, just like,
no real world responsibilities yet, just kind of.
coming in, and, especially that first, few weeks, first month, it's like everything is new. And it's just like, you're learning something every day. I mean, you're still learning something every day after.
Of course.
But
it's a different level, though.
Oh, this is like, this, like, I actually made, took an NMR, I actually got a spectrum
and all
like
the
how
peaks
I
are
had
beautiful
seen.
and sharp. They're beautiful and sharp.
Yeah,
right?
when you have that first, clean NMR spectrum, and it's like, oh, this is like, that problem they had on my exam, but I
Right.
made this. And it's like, it's pretty amazing.
So after your undergraduate experience, like you mentioned, you attended, you actually got an NSF, GRF. So, I'm sure that was really awesome to get that in the mail or, the email.
Yeah. So I didn't get it on my first application. So
Okay.
that was
also insightful to
was
hear.
my second one.
Yeah. So that's also insightful, because, if it doesn't work out, apply again,
Yeah.
But,
that's Gretzky, right? You miss 100% of the shots you don't take. A little Edmonton flavor there.
There you go. But yeah, so you attended Princeton and you did your graduate degree with, Professor Erik Sorenson there. You want to tell us a little bit about, the research that you did at Princeton, and maybe some of, like, I don't know, some advice kind of going through graduate school.
Yeah, I think so. So a big thing, just in sort of finding my way into Erik's group. So, and again, there was like a strong pull towards Erik's group when I got to Princeton, because Erik was actually Glenn's postdoc advisor. So,
Okay.
Glenn had spoken really positively about Erik, and that was a big reason why he suggested applying to Princeton. And the thing that Glenn brought up again and again is that he really, is that Erik is so enthusiastic about chemistry.
Right.
He's just really excited about doing chemistry. And I think I'll paraphrase it somewhat, but he also said something along the lines of, there isn't like a mean bone in Erik's body. He's just like a very positive kind of person. So, definitely I knew that, those things were sounding really good to me. But, I did try out a few different labs when I got to Princeton. Actually, my first rotation was in Brad Caro's group.
Oh, Brad.
Yeah. He was just starting out there. And, I think for me, it ended up being that I wanted to be slightly more on the organic side,
Yeah. Yeah.
and I think, Brad was bringing that really rigorous organometallic side, having
Yeah.
just come off of writing, the textbook with John. Um,
Very,
but
very hardcore organometallic
yeah,
chemists here.
but I
And
mean,
I,
beautiful
yeah.
chemistry, amazing ideas. But yeah, so I tried out a few different things, but it was really Erik's enthusiasm that drew me there. And I think two things really stood out to Erik or about Erik that I've really tried to keep in my own research group as well. Again, one is that Erik, you know, one thing that Erik said over and over again, and and that really sticks with me is that he said, I really want you to be able to love your project,
Yep.
to really have this, not just like, oh, you're assigned some project off an assembly line, because
Right.
his view of how you love a project is that you are, the biggest creative force behind it. So,
Yep.
he really believed in, people pursuing ideas, and he was there to help always, but,
Yep.
but really this idea that, I want you to love your project, and that the easiest way for that to happen is if you get to, have a huge amount of input on that.
Right.
So Erik was, so I guess the upshot of that is basically when I was in the group, Erik was pretty much game for anything. He's like, as long as you love the project and, and it, and, and you're really interested in it, like, let's see what happens. So,
That's a, yeah, that's a very, it's definitely a unique advising teaching style that
yeah,
definitely jives well with a lot of people.
right,
And there's
right.
definitely something about, yeah, I mean, loving your research project is arguably the most important aspect of it. It doesn't even really matter what, like, I feel like this is just, again, not my personal opinion, grain of salt, but I
Hmm.
feel like the science doesn't necessarily really matter, if that makes sense. Like the hardcore science
Yeah,
doesn't
yeah,
necessarily
yeah. The
matter.
specific question. Yeah,
Right. The specific question you're asking doesn't like necessarily matter. It seems like as long as
yeah,
you're
yeah,
loving it and like
yeah,
that's kind of the important thing because you're gonna
yeah.
spend 3-4 years doing it. So I don't
Yeah,
know.
no, I mean, I think one thing that, that really sort of positive outlook has really pushed me to do and to keep working on doing, again, is that there are like, you know, different things sort of wax and wane. Sometimes it is really hard and a slog, but, always trying to find some part of what you're doing that, you can love. Yeah, it might not be the specific question, maybe you're not as passionate at exploring the Hammett effect on this one sort of substrate effect, but finding some part of the process that is still interesting and is still exciting.
Yeah. Yeah.
Yeah,
So I'm seeing that you had kind of broadly worked on photochemistry, photocatalytic
yeah,
reactions
yeah.
using earth abundant elements and both. Okay, so both of those things I just said are in hindsight, like looking on it now, we know a lot more about it now. But I'm sure when you were a
Hmm.
graduate student, we still didn't really know a lot about photochemistry, photocatalytic reactions in that context. But also, even now, we don't really know. We're still learning a lot about earth abundant metals, right? So iron,
Right,
manganese,
right. Yeah,
cobalt,
yeah, yeah,
nickel.
yeah.
So, what was kind of your project and what was kind of maybe some of the conclusions coming towards the end of your time as a graduate student?
Yeah, yeah, no, for sure. So, interestingly, my project, I guess, sort of my first working project. So, my first year of graduate school, basically nothing worked, and that got thrown out and didn't make it into my thesis. but yeah, sort of after that. So one thing that was really cool that Erik was part of was this NSF Center for Selective CH Functionalization. So
Okay.
this was run by Hugh Davis out of Emory University. And
Okay.
basically, the NSF was giving funding, a little bit of funding to support research. But the biggest thing that it was trying to do was to create this community of people that were interested in functionalizing CH bonds. So,
Okay.
Hugh Davis was in this, Jin Kwan Yu, Momo Basagi, Brian Stoltz, lots of sort of organic people, Richmond Sarpong. And then one thing that was really cool about that is that we kind of had these. So every year there was an in-person meeting, and then every week, this was before COVID, and this was super like cutting edge. We had like a video meeting.
Yeah.
On I think on the software video that I don't even know if it exists anymore. But yeah, so every week we'd, come in and see somebody present. And what was really cool is that, again, you would see, some really organic talks, but yeah, you'd see much more inorganic chemistry as well from like, John Barry was in the center. Donna Blackman would talk about mechanism stuff and, just sort of being exposed to all this different kind of chemistry really got us all to start thinking about different things.
Mhm.
And, and one of these for me was, could we do like a CH aerolation? So like a CH like Minishi reaction or Minisky reaction. So that was kind of the like really sort of simple idea. So, I had this idea, maybe if we do it through radicals, we'll be able to do this cross dehydrogenative coupling. I went into the lab, and what I found is that the reaction didn't really work. So using this decatungstate, you could get like sub 1 turnover.
Okay.
Then the idea was, and then it's like I tried throwing in some co-catalyst to evolve hydrogen, because we need to remove those 2 hydrogen atoms to do a cross dehydrogenative coupling. So, let's try like, Adams catalyst, ruthenium, all of these different things. None of that worked. But what was really interesting is that we had just had this seminar from Jack Norton at Columbia, and he talked a lot about these cobalt complexes, cobalaxenes. The idea was, maybe we should try this cobalt catalyst because it can do hydrogen evolution. So I threw this in with the decatungstate. I was trying to add cyclohexane to pyridinium chloride.
Mhm.
And yeah, there was absolutely no cross dehydrogenative coupling. But what there was cyclohexene, which was pretty interesting. So you're going from cyclohexane to cyclohexene, which, is actually a pretty hard reaction.
Mm-hmm.
So, I saw that and it's like, this is pretty weird. So, tried a few different molecules and yeah, we were able to make alkenes from alkanes. And, Erik, again, Erik is known for total synthesis. He had done a little bit of methodology before I was there. But basically, I was like, hey, Erik, I found this really weird reaction, but I think it's pretty cool. And, and he's like, yeah, that is cool. Let's see what's happening.
Right.
So
it definitely is
yeah.
Not an easy process. Especially if
it's
you don't have any enzymes, it's pretty hard to do without.
Yeah. And again, I think one thing that was really cool is with that first observation, we actually thought about why does this reaction even work, and it turns out that again, the enzymes desaturase that do this kind of chemistry actually do a pretty similar radical mechanism.
Okay.
So this kind of idea of sort of sequentially plucking off hydrogen atoms, that's how desaturase works. And we had actually kind of fortuitously replicated that with this decatungstate, this tungsten photocatalyst, and this cobalaxene. So yeah, so that was a big part that's sort of like, I'd say, the key reaction from my graduate school,
Yeah.
or from my graduate career. We also did some other interesting things like, using uranium as a photocatalyst, but
Because why not?
uh yeah, well, because it solves some problems that decatungstate had, but yeah, I think, it was really, really cool, to sort of find this chemistry, but also then, to have that support and, opportunity to sort of follow up that initial result and figure out, why does this work? And also, why is this interesting?
Right.
I think like, especially coming in as an undergrad, I had this very kind of like narrow view of,
Mhm.
what a project should look like, again, like very much kind of top down, it's like,
Right.
we want to solve this problem. Here's the plan of action. We'll run these experiments and then the problem will be solved. They'll all work and then the problem will be solved. And, I think what was really cool about being in graduate school is it gave me that first kind of exposure to, sometimes the project comes from the chemistry,
Yep.
like you try to do something and it doesn't work, but the chemistry tells you something else. And that's even more interesting sometimes.
Yep.
So,
I
I think,
laughed there. I laughed
yeah,
there because of the how true it is. Like, I mean,
uh-huh.
people definitely have this perception of, especially as an undergrad. I mean, like, yeah, you have this top down view of like, yeah, we have this problem here, let's go solve it. But trust me, if it worked that way, there probably wouldn't be any more problems, honestly. I mean, so, but I think, and then there's also, it's kind of refreshing too. That's like, solving a problem for the kind of the chemistry sake of it, or like you're asking a question, like, are the problems that we're solving, like, are the problems that I'm solving gonna, are they gonna solve the cancer issue? No, but like, it's a chemistry problem, right?
Yeah,
So,
well, and they could be a step along that
right,
way. I really, at least in my experience, as both, starting from an undergrad all the way up until now, really, if as long as what you're seeing is new,
yeah,
it's going to matter to someone. It's going to be
right,
helpful to
very
someone.
true.
And actually, a big part of what I see my role, as an advisor, having usually more experience than people that, I'm advising, a big part of my role is to use that experience to say, this interesting observation that you made in the lab, this is going to matter to these people. And this is
Yeah,
going to help us to, when it comes time to write a paper, this is going to help us to, really make sure that that result that you found, gets seen by the people who are really going to be excited by it.
yeah, that's a really interesting point. Or idea, and concept, because it is true. I wish that there are contributions to that, maybe to in your own group are insignificant and negligible, but to other groups that's like, maybe it's like that's a key finding for them, or something like
Right,
that,
right.
So I wish, by the way, I do wish there was like some sort of depository of like just chemistry things we've tried. I don't know how else. I wish there was just like, here's everything that we tried. I couldn't get it to work or whatever. Feel free to take these results and
Yeah,
give
yeah.
it a shot yourself. But
Yeah,
I don't
yeah.
know. Maybe one of those. Maybe that'll come along one day. But
No, I mean, I think that would be, a huge benefit. And, and I think one thing that our group is trying to do more is to just include most, if not all of the data. Like,
yeah,
our papers have a lot of reactions that don't work
yep,
or work very poorly. And, and I think one of the really cool things about that is that really the reactions that don't work or barely work can sometimes teach you the most about the chemistry.
yeah,
Again, it's like the very first paper from our group, led by this awesome postdoc, Venkatesh Katamuri. You know, I'd say probably 60% of the paper is just discussing things that like don't work or barely work, because really it tells you like how the chemistry is working,
yeah,
which, and and gave us a lot of insights into how to actually use the reaction effectively.
Right. I think, again, this is my personal opinion for everyone that's listening out there, so take it with a grain of salt. But I feel like when you kind of read papers sometimes, it's almost like people are always trying to sell the applicability and the marketability as opposed to just talking about the science, like just talking about what's happening. And like, it's okay. I think it's okay to be like, that these substrates don't work or this doesn't work. We think for these reasons, and then that's just it. And then, well, I guess you could maybe say how you might fix that in a future publication. But I think that, like, I love reading those things, honestly. I don't, again, but this is kind of the pure chemistry point of view. I get how if you're a med chemist that this is not really important to you, but I don't know. It's just that's my opinion, but.
Yeah. Well, but I mean, again, that's like useful to medicinal chemists as well, to have a little bit more understanding of the reaction. And, and one other thing that was really an interesting thing that stuck with me in graduate school is once we were getting a presentation from a scientist at Merck. I think it was actually LC Campo. So he's, big and
farm to table.
Yep. Farm to table. Yeah.
Great
big
podcaster
as well. And I think, somebody asked him in a talk, about reaction optimization and, sort of what, pharma, expects from that, and how good of a reaction or how good does a reaction have to be for, pharma to care about it. And, again, I'll paraphrase because, this is like 10 years ago now, but LC said something along the lines of, it doesn't need to really be optimized, that much, or, or even if it has like really, strange scope or limited scope, as long as the reaction, the disconnection is interesting enough, like they'll try it, they will try with their system and see if they can get it to work. So, from that sort of view, like the most important thing is demonstrating the reactivity, and then trying to show like a preliminary understanding of, what works and what doesn't. So that's almost more useful than just a table of, 20 substrates that are all 90 plus, but, the 100 that are 0%, just left out of the paper, just sort of showing that, this might work, because again, pharma has all of the, high throughput experimentation, they can set up a screen super fast.
Right.
And,
it's good to keep in mind. So one other thing I wanted to ask you before I guess we kind of talk about your postdoc, but do you know Peter Waddle?
Yes. Yeah.
Yeah. He was, okay. I was just curious if you crossed paths with him. He's recently, well, I guess he's defending soon. But anyway,
wow, yeah,
he's defending soon. But I learned a lot of experimental chemistry from him. So shout out to Peter and here in our group.
Absolutely.
Just curious.
Yeah. I mean, I think that's one other thing that is really cool about going through grad school, postdoc, and undergrad is that. Yeah, you learn a ton from your coworkers as well. Yeah. Like the advisor has a huge effect on your experience, both like directly when they interact with you, but also indirectly with, what kind of lab environment there is.
Right.
But just the people that you're doing chemistry with every day, they teach you a lot.
Mm-hmm. Yeah. It's, some of the best chemistry techniques that I've learned are, from, not even from rad, they're from the senior level students and the postdocs that a little funny story. It's very mini, but I was a technique that I didn't even really think about, but our postdoc was using like a syringe with like a tube and on a frit. So like instead of using like a vacuum to pull down like the solvent, he's using a syringe and a tube. And I was like, oh my God, I never even thought about I was like, I never even thought about that.
Yeah,
so just like little things like that.
It makes a vacuum just the same, right?
Right. I thought it was really, I was like, oh my God, why do they never think of it about that? If, in case someone's using the vacuum or something. Anyway, just some little things that just like you see. Anyway, so After your graduate school, you did a postdoc with Professors Harry Gray and Brian Stoltz.
Yeah.
I think they're at Caltech, right? So
Uh-huh.
I guess it's kind of a two-part question. One is, thinking about postdoc. I mean, at this point, we really think about doing an academic career. And then also, too, what led you to do a postdoc at Caltech?
Right. Yeah. So really, really good questions. So yeah, I think one thing so I was considering an academic career, as I was coming up on the end of PhD, and really a big reason for that was even less sort of like, just the research questions. But, when I was at Princeton, outside of Erik's group, it was a pretty competitive place. Again, I sort of mentioned before, yeah, there were some groups where the, kind of expectation was like 72 hours a week. There were
Yeah.
some groups where, the PI did a walkthrough at 9 a.m. and 9 p.m. And
Yep.
again, it was like really, really kind of grinding.
Mm-hmm.
And, there was a lot of competition between a lot of the graduate students as well. And, and I think one thing that I got really passionate about, when I had that sort of revelation, that if I sort of step back, look after my health and, sort of all of me and my chemistry gets better, is that it's like, if I were to be a PI, I could try to do really, really good chemistry and do it, with the lessons that I learned in graduate school,
Right.
to sort of run the experiment and be a data point that shows that, you don't need to grind 70 hours a week to do cool science. So that was something that was like one of my biggest motivations, is that if I did academics, I would actually have that opportunity to, run that experiment. But, in order to do that, yeah, I needed to have a postdoc. It's more or less, expected in chemistry that, you do, even just a short postdoc before doing a faculty position. So for me, the number one and number two priorities of the postdoc. So the first non-negotiable priority was that, the postdoc advisor is a good person,
Right.
and
Fair play.
is supportive and, ideally enthusiastic, like Erik was. And then the number two, priority was, ideally I want to learn something in my postdoc, to actually gain some new kind of knowledge or approach. So the person that really, really stood out for that, for me was, particularly Harry Gray. So, again, a big name in inorganic chemistry, bioinorganic. And
I don't recognize that name. I'm gonna look this up real quick.
yeah, so yeah, Harry, he's so he did a lot of sort of ligand field theory. That was sort of like his postdoc. But yeah, he's, he did a lot of sort of solar fuel generation, a lot of sort of fundamental inorganic chemistry. And then, recently has looked a lot at like the bioinorganic chemistry of P450 and multi-copper oxidases. But yeah, very much from the sort of inorganic, let's think about what the metal is doing side. So I thought that'd be really cool. But, the biggest thing that Erik and everyone said is that Harry is super supportive and he is the most enthusiastic person. Like, if you ever have the chance to interact with Harry, it's it's like a sort of shot of chemistry adrenaline. He's just so excited about it. And he had supported a ton of people to go into academics. And I knew Brian from the CH Functionalization Center, and Brian was, again, really, really cared a lot about his group. And sort of my idea was, since I'm coming from such an organic background, if I come to Caltech, I can learn a lot of inorganic chemistry from Harry while still keeping one foot in organic chemistry with Brian.
Yeah.
So I was mostly in Harry's lab, but I still met with Brian a lot. And that was a really, really interesting experience. A lot of the chemistry. So I was trying to do some sort of heterogeneous electrocatalysis for things like CH oxidation.
Yeah.
The main lesson from that is that electrochemistry is really hard. Again, I think, beautiful work, early work from Kevin Muller, and recently Song Lin and Phil Barron and Shelley
Right.
Mintier, all of these other people, have sort of started to give us the lessons for, how to actually do these sort of preparative synthetic electrochemical reactions. But I would say that a lot of that understanding was still kind of evolving when I was starting. And so actually there were some really interesting results from my time at Caltech. But in terms of actually making a synthetic reaction, it was still a ways away when I left.
Yeah.
But what I really took from it, again, is just some more sort of management and kind of intangible aspects. And I think one thing that was really amazing, and actually really kind of healing about being at Caltech is so Harry Gray and Bob Grubbs, were both really, really good friends, both from Kentucky as well, and super famous. And what I found that was amazing and really inspiring is that, in a lot of graduate programs, sometimes there'll be some students, sometimes students will run into some sort of issue, with joining a lab, or they're in a lab and then they need to change, they need to leave it for whatever reason. I think that sometimes there can be a lot of, sort of judgment and stigma around that. But, I think what was really amazing, at Caltech is that the groups that, accepted these students that were leaving other groups were the Gray group and the Grubbs group, and these students would switch groups or, switch to these other groups, and they would do some amazing science, again, because both Harry and Bob, would basically say, like, you're at Caltech, I know you can do amazing research, and, and it's my job to, help you to do that. So, just being really open and just sort of like blanket supportive of people, and especially people that were going through, a pretty hard time in graduate school, and I think it's like, from the outside, it would be like, oh, these famous groups, they probably, have their pick of students, and, they only take, the best students, whatever that means. But, when I got there, it was actually, these super successful groups were the ones that were, really giving people a second chance and investing in people. And that was really, really cool.
Yeah. It definitely, my impression is, people have, this is the first time I'm personally heard about Harry Gray, but, Professor Bob Grubbs, obviously, I know plenty of people who've interacted with him, and it's always just, he was just a fantastic person. Then he was a great chemist too. So, just great people, great with people, right?
Well, and I think, again, one thing that I really took from that, as a PI is that I want to be a professor for all of my students, not just the ones that, have the working projects or, get all A's in their graduate courses or whatever. I want, everybody that joins our group, I really want to have a successful time.
Yeah, that's excellent to hear. And I was going to say, it seems like, some of the work you do now, you could definitely see how your experience from postdoc, the things on like metal to ligand charge transfer and radical transfer, like I could see how that is being carried over probably from your time and an inorganic kind of background. thinking about that. So that's really interesting. So I guess with that, we'll transition now. So now you're at Rice University, doing a lot of really cool work. Really with, a lot of areas. So earth abundant metals catalysis, this idea of cooperative hydrogen atom transfer, and a lot of work, doing azidation chemistry. So I'll kind of let you take the floor here and maybe give us a primer in your background. I do kind of want to start with this cooperative hydrogen atom transfer, because I was recently reading your publication on the, I guess, enantioselective.
Yeah, right.
Hydrogen atom transfer. So I definitely want to hear about this story and how far it's come, right? Because I saw you kind of first published it on 2019, 2020, and now you're starting to see enantioselectivities of this. So I don't know. I'll let you take the floor here.
Yeah. No, so, I think, again, kind of coming from, my time with Erik and then with Harry, a big part that I'm really passionate about in our group is, again, that, the chemistry is going to be driven by the people in our group. So, like 95% of our projects, really start with a student or a postdoc. But I'd say, as an advisor, when I'm talking, with members of our group, it's kind of like, let's find some interesting chemistry. I'm going to be most helpful if, the chemistry is somewhat connected to my experience. So, I've done a lot of radical chemistry, I've worked with metals. So usually we tend to sort of be in that very broad playground of radicals, first row transition metals. But, within that, really the biggest thing for me is seeing what the chemistry. Oh, let's see. Huh. Okay, it says. Okay. Did we drop out a little bit there?
I think we dropped out a little bit there, but I think I didn't get a message about anything stopping though.
Okay.
So
okay.
I think we're okay.
Yeah.
I think we're good.
Yeah. Okay. Yeah. No, I was just gonna say, is
that
a big thing that's important is seeing what the chemistry tells us, and then really trying to use our experience to figure out what what we can learn from this and who it's going to be exciting for. So, again, like for this cooperative hydrogen atom transfer, in some ways, we were thinking a lot about, hydrogen atom transfer when we were starting out, because, that's something that I'd done in a kind of oxidative sense as a graduate student, so, removing hydrogen atoms. And I was talking with Venkatesh, and we were kind of interested in, what if we're actually giving hydrogen atoms to the substrate? And so we were reading all these different papers, and Venkatesh found this really interesting paper in, I think it was JOC, on a hydrothylation using a cobalt catalyst. And what they had found is, they were using some cobalt catalyst, stoichiometric thiol, and under some conditions, instead of getting hydrothylation, they were getting actually the hydrogenation. And we were looking at the bond strengths, and we were thinking, it makes sense that we would make this kind of product because, this metal catalyst has a really weak MH bond. This is like less than 30 kcals per mole. So you should readily be able to reduce an olefin to the radical. And then thiols are really good at giving hydrogen atoms to those radicals. So again, they're really good at forming strong bonds of about 100 kcals per mole, because the bond strength of thiophenol is about 82. So the interesting thing would be is that we'd make this oxidizing thiol radical, and then actually by the metal doing this first hydrogen atom transfer, the metal actually gets formally reduced by 1 electron. So we have reduced metal, we have oxidizing thiol, And actually, if we reduced from one equivalent of thiol to catalytic, could these two come together and get back to their starting points? So thiolate plus hydrogen is thiol. Oxidized metal, you give it a hydride and you remake that metal hydride. So it's just kind of thinking, this is some interesting reactivity in the literature, but, can we actually think about how this is working and then, innovate in the catalysis? So Venkatesh was really, really enthusiastic, went into the lab, ran a bunch of reactions, and really in not too long, he came across that, iron and thiophenol together actually work pretty well for this reduction, and we were pretty much optimized for this reaction. We were ready to go for the substrate scope. And so I started in July 2019, July 1st, 2019. And so we were all ready to go. And it was, February 2020. And then our lab shut down.
Yeah.
So and I think what was really amazing and what I'm really grateful for our lab members is that, as we started opening up slowly, so, we had 3 months of shutdown completely, and then about another 9 months of 50%, is that Venkatesh really, worked super, super efficiently in, fleshing out the substrate scope. And, we were really, and, with his really, thoughtful, efficient, and resilient work, we actually published that in, I think, October of 2020. So,
Wow.
we were still 50%. But, I think one thing that Venkatesh did really well, that was a great role model for the rest of our group, is just modeling how to work efficiently, and that's not hours in the lab, but, it's like what you do with those hours. So,
Yeah.
you don't need to work 70 hours a week. This was like a clear demonstration of, if we're doing like, 7 hours a day times 5 days, 35 hours, you can publish a JAX paper. So,
Yeah, right. I'm
yeah.
looking. Yeah, I'm kind of looking at it now. What I really appreciate it. First of all, some of the substrates, so it's 6 days. It's kind of funny to me looking back at it. But that's just the chemistry, right? It's just kind of funny.
Yeah,
8
that's
days,
the chemistry.
I see 8 days here. That's hilarious. But also what I really like, though, is that you literally have a table of unsuccessful substrates, which I appreciate. So,
but again, often they teach us the most, and and I'd say that, again, that paper kind of showed us that, this kind of reaction might work. And then that gave us that sort of provisional understanding to, reach out to Scott Miller and Pat Holland at Yale and say, can we take advantage of, Scott's really amazing, platform of these sort of asymmetric thiols and actually start to introduce, some asymmetry into this reaction, while also, looking even closer at how some of these processes are working with Pat. And that was a really, really long running project. I think everybody says it, and it was certainly our experience that, asymmetric reactions are hard. There are a lot of variables, but, they can be really cool too. And so Venkatesh actually trained a new graduate student in our group during that time, Sarah Basaki, who's absolutely fantastic. And she, sort of took the baton and was the one who really pushed forward this asymmetric project, along with another really outstanding grad student at Yale, Savannah Mason, and a bunch of other, collaborators and coworkers who, had passed through all of our labs.
And as some of this is like a third party, this is a really cool publication, really cool paper, because we've hosted Pat Hollinger before at UH as one of our invited speakers. I mean, for the audience, you don't really know Pat Holland. I'm telling you right now, awesome inorganic chemist. Like, he really knows that fantastic work in iron chemistry, and I mean, probably one of the world's experts in just iron iron chemistry, honestly. Like, I mean, he's definitely up there. And then I don't really know Scott Miller, but I was, I'm sure using their platform and asymmetry was also just a really awesome like collaboration, honestly.
Yeah.
But also too, one other thing I want to say is I remember TechSyn 2022. I don't know if you were there, but it was hosted at UH, and I personally didn't interact with Sarah, but I know my buddy Justin, who's in our group, interacted with Sarah, and Sarah was telling about her research to him. So I kind of I'm hearing this through secondhand, but
right.
I guess my point is that it's really cool. This would have been May of 2022, right? So kind of seeing this kind of come full circle now it's really cool. It's one of those things that is, I'm sure, as someone who's actually participated in this, like it's so refreshing to see it all come full circle. I'm sure it's like it's a feeling that you really can't replicate. It's hard to explain.
I mean, I think it's something that that you get the chance to see, as a grad student as well, as a project going from that first hit or result, to a finished project. And I think, it is really a privilege as a advisor to, get to see that project or that, cycle again and again. And ideally, to be able to use my experience to make it a little bit smoother.
Right. Yeah. And I think what's really cool about it is you guys really kind of took the mechanistic approach here. And so I guess maybe you want to tell us a little bit about this. So what's happening here is you have an alkene, you want to induce some sort of asymmetry to get an anti-selective reduction of an alkene is essentially what's happening here. But you're using, really an earth abundant metal, an iron, to do this. And iron can be quite a difficult metal to work with. I mean, while it is true that it is, the most, it is quite literally the most abundant metal on Earth. Maybe. Oh, I think it definitely is. Right?
It's the most abundant transition,
and it's by far too. It's not even close, and it's dirt cheap. So if we could do a lot of these reactions with iron, I think everyone in the world would love to do this. But the fact of the matter is, it's really hard.
Well, I mean, if you think about it, iron is known in oxidation states from -2 to +6.
Yep.
And it'll go every single electron step between there. So it's it's definitely it's a little bit chaotic sometimes, but again, it's one of the things that or
go ahead. Go ahead.
Yeah. Well, I guess one of the things I hope that our research will do, particularly with these earth abundant elements like iron or cobalt or manganese, is that in addition to, doing an interesting transformation, ideally, these observations, including the results that don't work, will start to give us some lessons for, how we can actually use these first row metals predictably. We can actually start to design reactions, using these lessons that have a higher chance of working.
I think the other thing I was going to say is people that really aren't familiar with maybe the organometallics and maybe not that familiar with like the transition metal catalysis, but the reason why iron is just so far behind, as compared to like palladium and even nickel, honestly, at this point, it's just the intermediates are just not known for iron. I mean, no one. I feel like that's we're trying to get data, with all the Mossbauer spectroscopy, but I mean, it's so easy to isolate. I mean, it's relatively easy to isolate on cycle palladium catalysts, right? You can literally do that.
Right.
But with iron, you just can't. I mean, you can freeze trap and do Mossbauer, but you're not like, it's not like you get a crystal structure of these things, right? So,
I mean, if you're lucky sometimes, every once in a while, you'll get a crystal structure. But the other like big challenge of iron, and you mentioned it, is that, really for oxidation state, really your only option is Mossbauer. You don't have those nice, sort of UV vis spectroscopic handles that you do with like cobalt. So it's, so that was one reason why we were really excited to, be working with Pat on this, because, he has a huge amount of expertise in bringing all of these techniques to bear, Musbauer, EPR,
Right.
computational studies to support everything. And yeah, we had to throw all of that at this reaction to gain even more insight.
What's kind of been kind of seeing this come full circle now?
Mhm.
What's kind of been some of the biggest takeaways for you, like kind of from this experiment, this publication? What's kind of been, your biggest takeaways?
Yeah, again, I think, one big takeaway, I think that has been something that I've seen again and again as I've gone through my training is that, really that collaboration can be really enabling and rewarding. I think that in sort of historic organic chemistry, there's been a lot of reluctance to collaborate, particularly from the total synthesis side, where it's like different groups, racing to publish the molecule first and, protecting all of their results so they don't get scooped or whatever, that
Yeah.
sort of hyper competitive mindset. But yeah, I think for this, this most recent JAX paper, driven by Sarah and Savannah, again, none of this would have been possible without working together with Pat and Scott.
Yeah.
And, I think one other thing that's really interesting, or again, is that's sort of been reaffirming for us is that, I'm really, really proud of this paper, but, I think if you you could certainly have a very pessimistic read of this paper as well. So, again, it's like we did do asymmetric hydrogenation, which has never been done for this kind of radical, sort of reduction of alkenes. But, again, our like best enantioselectivities are, 80-20.
Right.
So
Which is
it's,
useful for pharma. So
yeah, well, it can be useful, especially if you have, SFC to support things. But again, I think just kind of, not having this very sort of surface level, oh, it's got to be 90% plus or it's
yeah.
useless or whatever. Because again, like also how the enantioselectivity varied taught us a lot about the reactivity and and what mattered and what's probably going on in the catalytic cycle. And just sort of, you know, looking at things kind of holistically beyond just a number, I think really gave us that space to do a lot of cool chemistry. So I think always, sort of maintaining that, optimism of, we can still learn something from all of these results, because I think definitely, talking to, some other organic chemists, sometimes it's like, oh, if it's not 90 plus EE, the project is dead. And it's like, you can still learn a lot.
Right. There's still a lot to be learned here. And really, I mean, you're laying the groundwork, the foundations. If people
Right,
want to
right.
increase the anti-selectivities, this is the groundwork
Yeah,
that needs to be
yeah.
done in order to do that, right? So,
Right, right.
um, definitely hear that. But another aspect of your research is, as I mentioned earlier, kind of the azidations, and this is something that's kind of curious to me because, um, maybe azidations. I guess okay, from the outside looking in, it's like, why do we care about azidations? I guess, but
Right,
maybe you
right.
could tell us a little bit about the chemistry itself, like what kind of, because I'm looking at this one right now, at least this idea of like the um little ligand to metal charge transfer to make this
Uh-huh.
happen.
Uh-huh.
So I'll let
Yeah, yeah.
you maybe speak on this a little bit. It's pretty cool, I
Yeah,
think.
yeah. Yeah. So first off, why do people care about azides? Particularly organic azides. So carbon, three nitrogens, sort of cumulene type structure. And a big reason is that traditionally azides have been used to make amines. So basically, again, you can reduce those with palladium and hydrogen. You can reduce those with phosphines. and yeah, so it's a really easy way to bring in that, sort of amine
Seems like an important
fragment.
synthon, I guess.
Yeah. Again, bioactive molecules, contain over 2 nitrogens per molecule on average. So so it's a great way to bring in nitrogen. It's also a great way to bring in a nice bioorthogonal handle. So, again, like sort of click chemistry, whether with copper or with these sort of strained alkynes. So again, this sort of recent Nobel Prize to,
No big deal.
Sharpless again, and, Bertozzi and Mendel. Yeah.
Yeah. Mm-hmm.
Yeah. All. So, there are reasons why azides could be useful, but, from the reactivity side, why we have really thought a lot about azides is because they're really good participants in in 2 kinds of processes, I guess. So you mentioned one of these, which is ligand to metal charge transfer. So basically, this idea of sort of inner sphere photocatalysis. So if you have some sort of MX linkage, so, some oxidized metal, some anionic ligand, depending on how you're assigning electrons. So, something like a halide or a pseudohalide. So azide is a pseudohalide. Is that if you hit these elements, particularly first row transition elements, so copper is really well known for this, but so is iron increasingly. You can photoexcite it, and then you can lead, either through the excitation or through some sort of intermediate excited state that it relaxes to. You can actually think about homolyzing that bond or bringing some bond breaking character into it. So if you have this metal ligand sigma bond, you can think about conceptually just breaking that in the middle. And it's a really good way to basically translate an anion, so something like azide, N3 minus, or chloride, Cl minus, into the radical. So N3 dot or Cl dot, under really mild conditions, basically room temperature, typically in acetonitrile or some solvent like that. You hit it with light, you break the bond, you make the radical. So it's a really, really mild way of making a radical, again, using earth abundant elements. But the other thing that got us really excited is this other kind of process, which our group has called radical ligand transfer, which is, again, really inspired by, again, bio-inorganic chemistry, chemistry like Harry thought a lot about at Caltech. And Jay Groves has done a lot of beautiful work here, Larry Kay at Minnesota, where basically if you have some sort of redox active metal, typically manganese or iron, with this X-type ligand, and a radical encounters it, this X-type ligand can basically rebound onto that radical with a simultaneous reduction of the metal center. So you go from X minus and you transfer it as if it was X dot.
Okay.
So this is a key step in P450 hydroxylation, so the radical rebound kind of mechanism. So it's known for HO minus hydroxide, but also beautiful work. And it's also known for halogens. So like the non-heme halogenases typically do this with, chlorine. So for CH chlorination in enzymes or bromination. And Jay Groves has done this with fluorination as well, using sort of biomimetic compounds. So the cool thing is that azide really readily participates in this radical ligand transfer chemistry as well. So it's a way to make C&N bonds. So one of the nice things about iron, like we were talking about, one of the challenges, but also one of the advantages is iron does a lot, And what's exciting is that iron does both this ligand to metal charge transfer and this radical ligand transfer. It can do both. So could we use both of these steps in some kind of catalytic cycle to, start making some valuable bonds? So that was something that 2 really amazing grad students in our group. So Kangji Bian, who goes by Harry, and Shije Kao. And they leveraged this to, add two azides to an alkene. So alkene diazidation. So that was in 2022, Nature Com. And then we sort of followed that up with, can we use LMCT to do a decarboxylation and then transfer this azide to basically replace CO2H with N3. So this sort of carbon to nitrogen swap.
Yeah.
And it's been really cool because, again, it's in this case, that sort of promiscuity of iron is super important. They can do all of these different mechanisms because we need it to do different kinds of processes.
Yeah, that's really interesting. And the hardcore kind of organometallics and the ligand to metal, all that's going on is really interesting to me personally. Not, necessarily the applications of this, but for me personally, that's really cool science.
Yeah.
As we kind of wrap up here, is there anything maybe people that are considering going to graduate school, what can they expect by being in the Professor Julian West lab at Rice? Like, what can you kind of expect and to do?
Yeah, no, I think that's a really good question. I think when students are coming to Rice, so Rice, we have a rotation system through the first semester. So students can try out a few different labs and, really see what speaks to them. And, with students in our group, that are rotating in our group, when I'm talking to the students, the main thing, my main expectations, I guess, as an advisor is that, people are curious about, the chemistry, they're interested in doing new kinds of chemistry and, broadly within catalysis or synthesis or mechanistic chemistry. So, so usually people are pretty down with that expectation, if they're coming to graduate school. But, then the other one that I'd say, again, calling back to my own experience as a grad student is, our work expectation is basically an average of 40 hours a week. So a sort of, standard work week that is flexible, basically, some people come in early, leave early. Some people come in late, leave late. But just to be sort of persistent, and to make sure that they're keeping up with things outside of the lab too, both for the better science, but also just because, I feel like it's the right thing to do.
Right.
And then, I think if people, again, if they're coming, they're curious and they, work persistently on the chemistry, that's how we've found all of the science in our group.
Yeah. Just, that is, I hope more groups kind of adopt this mindset, because I definitely agree with it. I feel like, I think if you're kind of averaging out about 50 hours a week, but they're good hours, like, you're constantly getting good sleep and eating well, physical health, and you're being consistent and persistent, like you say, then, the science will work out, I think. And so I definitely hear that. And hopefully people adopt that. Listen, of course, these aren't going to work for everyone, but that's just my general rule of thumb. You kind of make your own hours, but anyway.
Yeah. No, for sure.
Well, Julian, I want to thank you so much for coming on to the podcast. It was a pleasure chatting with you, and extremely insightful for the audience. So if you joined us for another episode, thank you again for listening. But we'll see you on the next episode.
Awesome. Thanks.